Assalamu alaikum dear student, this is Wajid Ali Shah, and today we will be discussing the topic Lenz's law, which is given on page number 152. Soon after the discovery of the Michael Faraday's law, it was thought that what will be the direction of induced EMF and induced current. So for that reason, we have Lenz's law. Lenz's law is a convenient alternative method for determining the direction of an induced EMF or current. Basically, it is the direction of the current which is important here in Lenz's law. But the current is basically the reason of induced EMF, so that's why sometimes people say that it is the direction of the EMF, but actually it is the direction of current. It always gives the same results as the sign rules we have introduced for EMF and rate of change of the magnetic flux in connection with Faraday's law, which has been explained in the previous topic. To find the direction of the induced current, German scientist Lenz proposed that the direction of the current or the induced current statement of the law is the induced current will flow in such a direction that will oppose the cause that produces it. According to this law, the direction of the current will always oppose its own creating cause. Or simply, we can state that the induced current produced as a result of the Michael Faraday's law of electromagnetic induction, this induced current will basically oppose the cause which is generating the current itself. To explain this, let me remind you an equation which we had already explained in previous topic, that minus n delta phi divided by delta t. This is in fact Michael Faraday's law of electromagnetic induction. In the previous lecture, we had discussed this negative sign briefly, but here we will explain this concept in detail. This negative sign reminds us that the induced current opposes the changing magnetic field that caused this induced current. This induced EMF will oppose the rate of change of magnetic flux. Resultantly, the current induced by this induced EMF will oppose this changing magnetic flux. As in physics, we have always been discussing this concept that in physics negative sign means opposition in direction. So, the direction of the induced EMF or the induced current will automatically be opposing the changing magnetic flux. So, induced EMF or induced current will never like to change the magnetic flux passing through the coil. To explain this concept, let us we have a small activity. An activity which we can also perform in physics lab, like we have a coil in which we have so many number of loops like this, a galvanometer attached to the loop, this needle of the galvanometer, a bar magnet, this is north side, this is south side. And for example, in first part of the experiment, we are moving the magnet towards the coil. So, according to this law, the motion of the bar magnet north side towards the coil is basically the reason of increasing flux across the coil, and to oppose that reason, the coil should be opposing the movement of the bar magnet towards the coil. So how this coil can be opposing the movement of this magnet? How is it possible? It's a bilateral concept, very much simple and easy concept. That when this bar magnet is moving towards the coil, north side is moving towards the coil, magnetic flux across the coil will be increasing. As the magnet is coming closer and closer to the coil, so flux will be increasing, intensity will be increasing. So this changing magnetic flux will induce a current in this coil, and because of that current induced in the coil, we have already discussed a concept of electromagnetism in the previous chapter. So this induced current in the coil will induce an additional magnetic field across this coil, and that magnetic field will behave to oppose the motion of the bar magnet towards the coil. So north will be repelled by this north. This north of the bar magnet will be repelled away by the north side of this coil. So because of this repulsion between the two same sides of the magnet, north-north repulsion, like poles repulsion, we are trying to move the magnet towards the coil, but this north will try to take this coil away, this bar magnet or coil away from each other. So this north side will give us the concept of the direction of the current induced in the coil. Now, what is that direction of the induced current in the coil, which can be found by the use of right hand rule, which we already had discussed in chapter number 3. Right hand rule used for a solenoid. We will use that concept here again. So, if this side becomes north, that will become south. So if this becomes north, so we can simply find the direction of the current by the use of right hand rule, like this. If this thumb shows the direction of north, so the curling finger will be showing the direction of the current, which comes out to be anti-clockwise in this case. It is by the use of right hand rule, previously discussed. Another case, another part of the same experiment, we have a galvanometer attached to the coil, magnet. This is north side, this is south side, this is coil, galvanometer. In second part of the experiment, if you want to take the magnet away from the coil, again the flux will be decreasing because the magnet is moving away and the strength of magnetic field will be decreasing, so magnetic flux will be decreasing. Again, magnetic flux is changing across the coil, current will be induced in the coil, which can be indicated, which can be shown by the deflection of the needle of galvanometer. Very much simple. But this time, the direction of the bar magnet is opposite to the previous case. In this case, we are moving magnet towards the coil, but in second part, we are taking the magnet away from the coil. Increasing flux, decreasing flux. This time again, an induced EMF, induced current will be produced in the coil, which can be seen by the deflection of the needle of the galvanometer. So, what happens here? According to Lenz's law, here the reason of inducing EMF or induced current is the motion of the magnet away from the coil. This is the reason. To oppose this motion of the magnet away from the coil, to oppose this motion of the bar magnet away from the coil, this side of the coil now becomes south, because unlike poles attract each other. Due to the attraction of this south side of the electromagnetic effect produced by the induced current, this south side of the electromagnetic effect produced by the induced current will try to attract the north side towards itself, again opposing the motion of the magnet away. So this south will give us the idea of the direction of the current. How? By the use of same right hand rule, which we had already discussed in previous chapter. This time, if this side becomes south, so the opposite side will be north. So we will extend the thumb in direction of the north, like this, like this, like this. This one. This is north, so the curling finger will give direction of the current. This time direction of the current comes out to be clockwise. This is Lenz's law. The direction of the current is such that it will always oppose the reason, the cause of the generating EMF or the current itself. This is according to Lenz's law. Lenz's law is totally in accordance with the law of conservation of energy. Law of conservation is basically another form, modified form, manifestation of the law of conservation of energy. In the above case, for example, when the end pole of the magnet is approaching the coil, like in this one, the induced current will flow in the coil in such a direction that the left hand face of the coil becomes north pole, this one. The result is that the motion of the magnet is opposed, north-north opposition, repulsion. The mechanical energy spent in overcoming this opposition is converted into electrical energy, which appears in the coil. We are actually doing work on the magnet to make it move towards the coil. The coil is opposing us, so the energy consumed by us will be converting into electrical energy. This is called Lenz's law, and it is totally according to the law of conservation of energy. Thank you. Have a nice day.